Voltaic cells. We'll talk about electricity some more. So electrical current is the flow of electric charge. So basically what that means is it's electrons moving from one place to another. That's what electricity is. And redox reactions can be used to generate electric current. So the example we're going to look at first is zinc metal reacting with copper 2+ ions to form zinc ions in solid copper metal. Zinc has a greater tendency to lose electrons than copper does. And so what will happen is the zinc atom will transfer 2 electrons to the copper ion. The copper ion then becomes a copper atom. The zinc atom becomes an ion and dissolves into the solution. The copper ion becomes an atom and deposits onto the zinc as solid copper. And here's an illustration in pictures. So here's the copper sulfate solution, that pretty blue solution, and you put a strip of zinc in there, and this is a spontaneous reaction. And you see the shiny zinc getting all crusty and clumpy. It looks like it's got miniature barnacles on it or something. And do you see the color of this solution?
It's lighter.
It's lighter. And if you wait long enough, it'll become clear. All of the copper ions will precipitate as copper atoms onto the zinc.
And zinc in solution has no color.
Zinc in solution doesn't have a color, no. And so here's the illustration of what's going on here. The copper ions come up to the zinc metal. The zinc gives them 2 electrons. They become atoms, which are no longer soluble in water. And since they were right there getting the electrons, they just stay there. Now the zinc has a charge, and so it takes off. So the zinc is gradually eaten away, and then the copper deposits on it. Now it's not depositing in a very beautiful fashion, but it's copper. Yes?
How quick does that happen?
It happens fairly quickly, actually.
Really? Like I can watch it happen?
You can watch it happen, yeah.
Because we have copper sulfate coming out of our ears at work.
Yeah.
I would love to see that happen.
Just put a piece of zinc in there. Now, if you put a strip of copper into a solution with zinc ions,
Nothing's going to happen.
nothing happens.
You have to put energy into it.
You would have to put energy into it to make that happen. Because zinc has a greater tendency to give up electrons than copper does. So, in that situation with the zinc metal in the beaker, the electron transfer was direct from the atom to the ion. If we separate the zinc atoms and the copper ions, the transfer can still take place if we provide a connection for the electrons to flow through, like a wire. And the electrons will go through the wire, and electrons going through a wire is what? Electric current. It's electricity. So, what we call an electrochemical cell is a device in which a chemical reaction either produces electricity or is caused to happen by an electrical current. So there's 2 types of electrochemical cells. There's a voltaic cell, sometimes called a galvanic cell, and this is one where we produce electricity from a spontaneous reaction. An electrolytic cell consumes electric current to drive a non-spontaneous chemical reaction. Yes?
So if we have that, like it's the battery, right? That cell, and so it'll push, if we have that connected right here, it'll push current from here to here, right? But if we force it to go the opposite way, does that take a voltaic cell and turn it into an electrolytic cell?
Yeah,
If we force it the opposite way?
if you were going to put the copper metal in a solution of zinc, and it's not going to do anything, right?
Yeah.
But if you apply an electric force across it,
Yeah.
you can force it to react. So you can make a non-spontaneous reaction proceed
So,
using electrical energy.
but you can take that electrolyte, that's the electrolytic cell, and you force that reaction, and you stop that.
And you can make
use
it go
as
backwards.
voltaic.
Yeah.
Now it's a voltaic cell. Cool.
Yeah, back and forth, back and forth. But each back and forth, heat tax.
Yeah.
And batteries are voltaic cells. And if they're designed properly, they can be recharged. You put electricity across them and you just force the reaction to go back. And then you can stick it back into whatever your device is and it'll go forward again and generate electricity. But you lose energy each time you charge the battery. So here's an illustration of a voltaic cell. So here we have a strip of zinc metal in a solution of zinc nitrate. Nitrate is a common anion because all nitrate compounds are soluble, so that's always good. So we've got a strip of each metal, those are called electrodes, placed in a solution of its ions to form a half cell. So we've got the zinc in zinc nitrate, we've got copper in copper 2 nitrate. And we've got an oxidation half reaction and a reduction half reaction. This is going to form an equilibrium between zinc and zinc 2+ ions. And the copper also, there will be an equilibrium here. The zinc has a greater tendency to ionize, and so its equilibrium is going to lie further to the right. And the copper does not have as great a tendency, and so it's going to, instead of favoring the ion, it's going to favor the metal. So the zinc electrode is going to be negative relative to the copper electrode. So if we connect these half cells with a wire, and here we threw in a light bulb just for fun, then the electrons are going to flow away from the zinc electrode, which is negative, and they're going to flow towards the copper electrode, which is more positive. Electrons are repelled by negative charges, they're attracted by positive charges. And when that happens, then this equilibrium shifts even farther to the right, and it just keeps shifting and providing more electrons, and these electrons leave, and it shifts more. And over here, electrons are coming in. Putting electrons in shifts this towards the copper metal.
I have a question.
Yes?
So when the zinc, it dissolves.
Mhm.
So you're losing some of that zinc plate into the liquid.
Yes.
Like more it goes. Does where it comes off of that plate, does it have a preference?
That's a good question. The outside.
Yeah. So like it's dunked in the liquid, so it will come off right at the top of the liquid, like so it travels the charge has to travel less on the surface. Or less on
That's
the
a good question. I really don't know the answer to that.
I mean, like
There's a lot of different factors that would play into that.
Okay.
Yeah. Any other questions? The salt bridge. We're going to talk about the salt bridge in a minute. But if we think about this, so electrons are going from the zinc side to the copper side. That's going to give us a big buildup of electrons over there, of negative charge here and positive charge here. Nature doesn't like positive and negative charges to be separated like that. So if there was no salt bridge here, the electric current would flow a tiny bit forward and stop. Because now we'd have too many negative charges over here, and nothing would happen anymore. So we have to allow a way for negative charge to return. And that happens through this salt bridge that we'll talk about in a minute. So electrical current is kind of a weird thing to think about, electrons moving through a wire. But it acts a lot like water flowing in a stream. And I think at the very least, we've all played around with water running down the ditch, right? Down the gutter in the street. And we see that it's flowing. So the rate of electrons flowing is analogous to the rate of water flowing in a stream. And of course, we need units for these things. So ampere, which is abbreviated with a capital A, is a unit of electrical current. And it's also sometimes just called amp. So, 5 amps or, 30 milliamp charger. It's the electric current that's being measured. Another unit is Coulomb. Coulomb is a unit of electrical charge. In chemistry, we often talk about electrons being -1 and protons being +1, and we just have these relative charges. But Coulomb is an actual unit that measures charge. And an electron has a very, very small charge in terms of coulombs. So an amp is a measure of charge per second, just like a rate of speed. How many miles per hour, how many gallons of water per minute are coming out of the dam, right? So an amp is 1 coulomb per second. And just if you're interested, that's equivalent to 6 × 10⁸ electrons per second. Water current is driven by a difference in gravitational potential energy. Water runs from something higher to something lower. And the steeper the grade, the faster the water runs, right?
Yes.
Well, electrical current is driven by a potential difference. And a potential difference is a difference in the potential energy per unit of charge. It's just a way of measuring that. And so volt is is the unit used to measure potential difference. 1 volt is 1 joule per coulomb. So if you have a larger difference in volts, you're going to most likely have a higher current. So large potential difference would be a large difference in charge between the two electrodes, and you'd have a strong tendency for electric current to flow, for electrons to flow. Just like if you have a very steep stream bed, the water's going to flow more quickly than it will on a more shallow stream bed. So the electrons are flowing. If this charge difference is larger, they're going to flow more strongly. Another term that you sometimes see is electromotive force, or EMF. Sometimes people talk about EMF fields, they're concerned that it's going to damage their health or something. Electromotive force. So it's a force that results in the motion of electrons. That's what electromotive force is. Just another word for potential difference. So the cell potential, which is abbreviated E cell, so this is a potential difference in the cell, or sometimes called the cell EMF, is the potential difference between the two electrodes in a voltaic cell. It's going to depend on the relative tendencies of the reactants to undergo oxidation and reduction. You'll get a real high positive cell potential if you've got something that has a high tendency towards reduction paired with something that has a high tendency towards oxidation. So you've got something that really wants to get electrons, paired with something that really wants to give electrons up. Things are going to go really, really smoothly. If you've got two substances that are kind of hesitant about this whole giving up and taking electrons, it's going to go really, really slowly. It's just not much going to happen. So it depends on that, and it also depends on the concentrations of your reactants and products, and it depends on the temperature. Usually all these things are going to happen at 25 degrees Celsius unless we specify otherwise. So standard cell potential, this is like we saw with standard entropy and standard enthalpy and all those guys. The 0 here means standard. And standard means that the concentrations of solutions are 1 molar. If there's anything in the gas phase, it's going to have a pressure of 1 atmosphere. So pretty much the same definitions that we used before. So for that first voltaic cell that we were talking about with the zinc and the copper, the standard cell potential for this is plus 1.10 volts. If we take the zinc out and replace it with nickel, nickel has a lower tendency to be oxidized. It's not as crazy about giving up electrons. It's more reluctant to do that. So we put a nickel electrode in there instead. The standard cell potential is going to drop to plus 0.62 volts. just because nickel does not give up its electrons as easily as zinc does. If you have a negative cell potential, minus 0.62, that means that the forward reaction is not spontaneous. If you took this reaction and turned it around, it would be negative 0.62. And that would mean that in order to have that reaction occur, you would have to supply a potential difference using a battery. So we've got these terms, and we have to keep them straight. We've got oxidation, we've got reduction, we've got electrons moving around, we've got anodes and cathodes. Oxidation occurs at the anode. And one way to remember that is both of those start with vowels. Reduction occurs at the cathode. Those both start with consonants. Or you can think about a red cat. A red an, it doesn't make much sense, right? So these are things that I've come up with to keep these straight in my head. If you've got some other way of doing it, that's fine. Oxidation occurs at the anode. Reduction occurs at the cathode. The anode is going to be more negatively charged than the cathode. It does not necessarily have a negative charge, but it is more negative than the cathode. And one way to remember this is the anode, that word is very similar to anion, right? And hopefully we all have straight that anions are negative. If we don't have that straight yet, we're in trouble. So anions are negative. The anode is more negatively charged. The cathode is more positively charged. Cations are positive. So the electrons are always going to flow from the anode to the cathode. The anode is more negative. Electrons are negative. They are repelled by that negative charge. They're attracted to the positive charge of the cathode. So they're going to flow from the anode to the cathode. If we only had electrons going from the anode to the cathode, we kind of got ahead of ourselves a little earlier, things wouldn't keep going. We get a buildup of charge. And so here we get to the salt bridge. The salt bridge allows the counterions, like the nitrate, it allows the counterions to flow between the half cells without the half cells actually mixing together. Because if we had all of this happening in one beaker, the electrons would not go through the wire. And then what's the point, right? We have to keep them separate so that we can use them going through the wire to light a light bulb or do whatever we want.
Why would
Yes.
they rather do that instead of going through the wires? Why wouldn't they just use the salt bridge and go backwards as opposed to go through the wire and go around?
Well, they're not going to go through the salt bridge, but if we have the zinc and the copper ions in the same container,
Yeah.
the transfer of electrons will be from the atom to the ion.
Mm-hmm.
And they won't go through a wire because they're just right next to each other. So we're separating them, and then they have to go through the wire. Question?
For this salt bridge,
Mm-hmm.
you said there's like a flow of counterions.
Mm-hmm.
Is it actually ions coming from this side going to that side, or is it just the liquid that's inside this separating its charge?
It's actually ions moving
From here?
from one side to the other. The salt bridge is usually a U-shaped tube. So chemists were using U-tubes a long time ago.
Oh.
Right. It's a U-shaped tube, and it has a strong electrolyte in it. Usually it's got some sort of a gel in it, kind of like gelatin, with like potassium nitrate or something in there. So a strong electrolyte. And what happens then is that the negative ions that are in the salt bridge, so if it was potassium nitrate, the nitrate ions could flow to neutralize the accumulation of positive charge at the anode. And then the positive ions, the potassium ions, can flow the other direction to neutralize the negative charge.
Right there, kind of what I see. Like it's the things inside the tube that are separating, not something coming from this beaker going to that beaker.
Well, so potassium ions are going in this direction.
Yes.
But if all the potassium ions in here moved over here, then it would have to stop.
Yeah.
So ions from here eventually are going to work their way up and in. Yeah. But you have to start with something in here to help it get going. Because pure water doesn't conduct electricity very well. So the potassium ions go this way and the nitrate ions go that way.
So what happens when it runs out of potassium ions?
Well, when it runs out of potassium ions, because what do you have going on over here? The zinc is giving up 2 electrons and becoming zinc ions, right? They will work their way into here eventually and travel around. And so it'll pretty much keep going until your zinc is gone or until the copper ions over here are gone. And then it'll stop. It'll slow down, though, because it is dependent on concentration as well. Any questions? We have a shorthand way of representing electrochemical cells. It's called a cell diagram or line notation. So that cell that we were looking at, we're going to put the oxidation half reaction on the left side and the reduction reaction on the right side. And so we've got zinc and zinc ions. And we separate them with a vertical line because this one's a solid and this one's aqueous. And over here we've got copper ions and solid copper, and those are separated with a vertical line because their phases are different. And then in between the two half reactions, we put a double vertical line. And that sort of represents the salt bridge, if that helps you remember. The double line goes in the middle, separating the two half reactions. Sometimes you do have both of these being aqueous, and then instead of a vertical line, you separate them with a comma. So let's look at an example. So here's a different electrochemical cell. So we've got iron and permanganate ion. This is in an acidic solution, and we're getting iron 2 ions and manganese 2 ions and water. So what are the two half reactions? Which one is oxidation? What's happening with the oxidation?
Iron?
Iron is going from a 0 oxidation state to a +2, right? So we've got iron solid going to iron 2+ aqueous, and that's going to have 2 electrons. Oxidation is loss of electrons. And what's being reduced? The permanganate, the manganese in the permanganate. Oops, not a plus. An arrow.
Process of elimination.
Yeah, process of elimination. It works well sometimes. So we could finish that out, but it's getting late and I don't feel like it. There's going to be some electrons on this side, right?
Yeah.
We could figure that out, but we don't feel like it.
So when you do this part, you don't have to worry about coefficients either at this point.
No, in the line notation, there are no coefficients. So here we have the oxidation reaction is first, and then the reduction. So oxidation, we've got iron that's a solid and iron 2 ions, that's aqueous. So they're separated by a vertical line. Here we've got the representation of the salt bridge in between. And then over here, we have the permanganate and hydrogen ion and the manganese
And plutonium.
and platinum.
Oh, platinum.
So
Yeah.
here we have the permanganate and the manganese ion. Those are both aqueous. Okay, those are both aqueous. And so they're separated with commas. And the hydrogen is in there as well. So we had permanganate and hydrogen ions, and over here we had manganese. We don't need to include the water in there at all. We probably should have finished this. Dang it. What would that be?
Why is there platinum?
I'll get to the platinum in a minute. What? 8 H pluses?
Yeah. Maybe more teachers should do
And then I need, this is 7, I need 5 electrons. So that's why there's H plus in there. So these are all aqueous, they're separated with commas. Well, you have to have something in there that's going to conduct the electricity out of the half cell. So that's what the platinum is. Platinum is very inert. So there's a line here, we have to have something that's a solid to hook our wire up to. So we use platinum. And it's not going to undergo any chemical reaction, it's just going to sit there unchanged and let electrons go through it.
Could that also be gold or?
You could also use gold or well, copper reacts with a bunch of things.
Yeah, but it's the wire.
It's common for a wire, but.
Yeah, but if you stick it in there with zinc, things are going to happen. So another one that's sometimes used is carbon.
Yeah, but it's the
Carbon rods conduct electricity as well.
Oh, yeah.
Yeah. Okay? So that's the line notation. So this is an illustration of that cell. Here we've got the iron electrode in a solution of iron ions. That's the oxidation. And over here we've got a platinum electrode because the things being reduced over here are aqueous. And then the salt bridge allows us to equalize the charges.
Could you use a solid manganese plate?
You could use manganese. It might undergo some other reaction, though.
It would turn into the Mn+2 and.
It would not just turn into Mn+2 by itself, no. But usually we're going to use something like platinum or carbon just to keep things simple.
Very nice.